This meeting is being recorded.
In this next video from chapter 19 on electrochemistry, we're going to relate how the potential found from a voltaic cell can be related to spontaneous change. And later on, we look at how this is also related to equilibrium. But you might have recalled in chapter 18 that you found a reaction to be spontaneous depending on the delta G, the Gibbs free energy. So this, we saw that if delta G was positive, we had a non-spontaneous reaction. And that if delta G was negative, we had a spontaneous reaction under certain conditions. But we can also relate the cell potential, which we reviewed in the last video, this E value here, to the Gibbs free energy of our system, which we know is the amount of work that a cell can do. So in this scenario here, so our delta G is the maximum amount of work a system can do. And that's what we're going to exploit here. We're going to find out if our reaction will be spontaneous by relating this E value, the cell potential, the N seen in this equation here, this delta G equation, references the number of moles of electrons that are transferred or moved during these redox reactions. F here, this is going to be a constant called the Faraday constant, and this is equal to this value here. 1 Faraday is 96,485 coulombs per mole. But we also know this is equal to 96,485 joules per volt mole, because we know that 1 coulomb is equal to 1 joule per volt. This equation here, this relationship of coulombs to joule volts, this may come in handy during some of our calculations. But let's look at this equation again. So under standard conditions, so when we have standardized temperature and pressure and other conditions such as molarity, our system can be measured and we can find our E cell, our cell potential under standard conditions. That's what this degree symbol up top here means, this naught. This little circle here, this means that we're at standard conditions. So again, at standard conditions, we can make some assumptions down here. We can say that when our E cell is found to be positive, based on this equation, we're going to see that our delta G will be negative, and then we'll have a spontaneous reaction. In the second set of conditions here, when E cell is negative, that would make that equation generate a positive delta G value, or Gibbs free energy, and that would imply a non-spontaneous reaction. And then this last case here, when E cell is found to be 0, this implies that our system is at equilibrium, and therefore our delta G, the Gibbs free energy, is going to be equal to 0. So let's keep these three cases in mind, and let's take a look at sample exercise 8 here. And we're asked to figure out if this reaction, as it's written right here, would occur spontaneously for standard state conditions. So again, standard state applies. Let's see here. So step 1, we'll have to balance our half reaction. So let me break this into two equations. So I have Cu2 plus, and then that would have to be plus 2 electrons. That will give me my solid copper. So this is going to be my reduction half equation because I'm adding electrons. And then my oxidation equation must be this, 2Fe2 plus. It's going to yield 2Fe 3 plus, and then 2 electrons were lost in this oxidation equation. So that's the same as the amount of electrons that were gained in our reduction. So now we know that this is going to be our cathode. This equation over here at the it will be at the anode, and that'll represent my oxidation equation. So I I'll go to my table now and I'll look up the values for my cathode and anode. And if you recall, my E cell standard state is going to be the E cat minus E anode. And I've already looked these up. So at the cathode, we're going to see 0.34 volts. And then at our anode, that reduction potential is going to be 0.77 volts. But we're going to subtract that value, right? This negative, rather, 0.77 here. When we do that, we're going to have a negative cell potential. So our E cell is negative 0.43 volts here. We would know that if we plug that into a delta G equation, we had a negative NF and then times this negative 4.3, we're going to get a positive delta G. So we know that this is a non-spontaneous reaction in the way that it's written in the equation. Our cell potential is a negative value, so we expect that to show. And then say we wanted to solve numerically for delta G. We're not asked here to do that. All we're asked is to determine this cell potential, and then really we're only asked to make the determination if it's spontaneous or not. So we've done that. But say we wanted to solve for delta G, we could use either this equation that we've seen in this chapter, negative RT ln K when we're at equilibrium, or we could use this equation here, negative NF E cell.